Welcome everyone to Scheller Lunchtime Live, a live stream series hosted by the Georgia Tech Scheller College of Business. My name is Lindsay Kane, and I'm the Associate Director of Client Relationships for non-degree executive education programs. On select Fridays at 12 p.m. Eastern, you'll have the chance to hear from Scheller faculty, student, and alumni speakers as they discuss relevant topics for the tech-driven digital age. At Scheller, we're proud to offer undergraduate, MBA, and PhD programs, along with open enrollment and custom executive education programs. It's my pleasure to introduce Dr. Robbie Moon, the Thomas Williams Wells Fargo Professor in Management. Robbie is an associate professor with research interests in financial accounting and auditing. He works on a variety of research topics relating to firms' voluntary and mandatory disclosures, non-traditional disclosures such as social media, and the intersection of audit and financial accounting research. Robbie's research often employs advanced analytical methods such as machine learning and natural language processing techniques. Robbie has also been published in all of the premier accounting journals. Prior to entering academics, he worked for 4 years in the advisory practice at KPMG in the firm's Atlanta office, and previously held both CPA and CIA certifications. Today, Robbie will discuss some of the basic strategies of NLP, including both traditional approaches and more recent advances in machine learning. He will use both practical and research-based examples to illustrate the power of text as data. As always, feel free to ask questions in the comments section. Robbie will address as many questions as possible at the end of this presentation. Over to you, Robbie.
Thank you, Lindsay. So thanks for joining us today. Some of you might wonder what an accounting professor is doing talking about things like advanced analytics and natural language processing. But as Lindsay alluded to, I use this a lot in my research, and I've recently been able to bring it into the classroom as well, because I teach an analytics class here at Scheller. So I hope I can give you some examples that kind of illustrate, how this can be useful for, your analytics problems. All right, so my plan for today is to first talk about what I mean as text as data. Right, so I'll talk about kind of the explosion of data, which I'm sure we've heard a lot about over the last several years, and then why at least I view most of this as, or a lot of this as something that's useful for natural language processing. I'll then talk about what I mean by NLP or natural language processing, and I'll split this into kind of two separate groups. I'll talk about the traditional approaches to NLP, which really started as early as the 1940s, 1950s, when scientists and analysts first wanted to take spoken language and figure out how to put it, get it in a form that could be analyzed by a computer. And then I'll talk about more recent advances with NLP and machine learning, which we interact with in our day-to-day lives, as I'll kind of illustrate. But then I'll show how these same techniques can be used to kind of update the procedures that we use in the more traditional approaches to give us more powerful insights. And then, time permitting, we'll hopefully be able to answer some of your questions. So this version of this quote has been floating around for the last 5 or 10 years. The version I found is it was Hal Varian, the chief economist at Google, I think sometime in 2010. Well, I'll go ahead and read it. It says, between the dawn of civilization in 2003, we only created 5 exabytes of data. Now we're creating that amount every 2 days. And by 2020, that figure is predicted to sit at 53 zettabytes, learning new volumes of information, or 53 trillion gigabytes, an increase of 50 times. So, like I said, there's several versions of this floating around. These exact numbers people will disagree on, but I think everyone agrees that the volume of information that's being created every day, or the volume of data that's being created every day, has just exploded over the last decade, over the last 2 decades, which is kind of what they call this the information age. So what does this data look like? Well, when I first think of data, a lot of times I think of something like an Excel spreadsheet. I know if I have some data that I want to organize, this might be the first app I open up and kind of organize it in here. And then I can do some basic analysis with it, maybe run some pivot tables. You look at means, medians, that kind of stuff. This is a small minority of the data that's out there. A lot of the data is going to take a form that looks something more like this, still kind of structured in this tabular form. But I would refer to this as maybe like trace data. Now, I've admittedly found this on Google Images, so I'm not going to tell you exactly what the source is, but it seems like it's maybe some kind of instantiation of a cloud-based server or something like that, where every time something happens on this platform, it's collecting data about it and tracking it. And so the trace data means it's kind of tracking all these trace actions that are taken. There's lots of versions of trace data with cell phones, really with any kind of system that you log into and do different things. That data is collected, and that data can get very big over time, right? Especially if it's collecting every user's every action. So that represents a large portion of the structured data that's out there. Obviously, web pages are a huge part of the internet. Web pages again account for a lot of the data that we see, or accounting for this growth that the previous quote alluded to. And then I do accounting research. I look at financial markets, so the amount of data available, both related to stock trading, stock quotes, is huge, as well as kind of information about these stocks. And so now one thing that all of these sources have in common is they tend to be relatively structured, and we have pretty good tools to analyze them. Now, most trace data, stock data, a lot of that is going to be too big to look at in something like Excel. But if you have some experience with SQL queries or maybe Python or R, really it's just a matter of loading that data in, provided you have a computer with enough resources, and then you can conduct an array of analyses. Now with HTML, maybe this isn't something that directly drops into kind of the tabular Excel-like form, but it still has this formatting or this structure that allows us to programmatically analyze it in a relatively straightforward manner. So this plot illustrates, again, the quote that I showed earlier. What I think is interesting about this plot is everything on the previous slide, maybe with one exception being the HTML data, is what I would call structured, which is this small amount, these small rectangles down here, this blue data. So the vast majority of data that's created every day that accounts for this kind of label of the information age is in this big orange piece right here, which is what I refer to as unstructured data. So what is unstructured data? Well, it's going to be things like images, videos, audio, and then text, right? And so what I'm going to talk to you today is how to take the text piece of this, or the written words, and what kind of techniques we can use to translate that into a structured data that we can analyze. So what are some examples of this text? Well, the first example here, I just pulled up the Wall Street Journal today. This is an article today on the Wall Street Journal. So this, if you think about text on the internet, maybe this is the first kind of thing you think about. So how many articles are produced each year? Like, what's the contribution of this towards the 50 zettabytes or whatever that number was? Difficult to pin down that exact number. I think it depends on what you consider to be, quote unquote, the press. I did find something that said the New York Times publishes about 1,000 articles per week online, so call that about 50,000 a year. You can imagine Wall Street Journal's maybe a little bit more than that. So among the mainstream media, we're probably in a few million articles per year. But if you expand this to include, kind of crowdsourced sites like Seeking Alpha, blogs, Medium, all those different sites that kind of are user-generated content, we're going to easily be into the hundreds of millions of pieces of unique documents, unique information that's out there available for analysis. A second example, this is just a snippet of an earnings call transcript. So this is something I've done a bit of research on. We look at firms' earnings call transcripts, look at the language that's used in those, and answer various questions. So I believe this is from Levi Strauss, and so this is actually spoken language, but these calls are very important to investors, very important to analysts, and so they're immediately transcribed and published, and for the most part available to the public. And so we have this large volume of spoken language that's transcribed and put out there. Now, earnings call transcripts are not the only kind of transcript. I don't know if this is big enough for you to read, but this is actually a wiretap. And if anyone's a basketball fan, you might recognize this Dawkins name. Unfortunately, I'm an LSU fan, so our coach was part of that as well. So this is another type of kind of transcribed data that, again, is accounting for this volume of data. Now, admittedly, wiretaps don't usually make it into the public domain until the The judicial process is complete, but there's lots of other transcripts, like court transcripts, that you'll find online and that account for a large part of the data. Social media accounts for a huge volume of information that the companies or individuals can use to answer questions. This is obviously Twitter. So how many tweets are generated? I had to look this up. In 2020, it was about 6,000 tweets per second, which corresponds to about 200 billion tweets over the course of a year. So obviously huge amounts of data that has information in it, but it's in this unstructured, this natural language format. And then finally, emails. There's about 300, in 2020, there were about 300 billion emails sent. Now, generally, these aren't public. I don't know if anyone can read that. This is from Enron. So there's a database of Enron emails out there, if you're interested in doing some analysis on that. But nonetheless, this is still data that accounts for a portion of the 50 zettabytes of data. So we've talked about this being data. Do we consider this to be information? And I think the answer is yes, but we need to have some kind of tool that can convert this vast amount of text, this vast amount of data, into something that is analyzable. So that's where this kind of set of tools comes in that I refer to as natural language processing. So what's the definition of natural language processing? Really, it's the ability of the computer program or computer script to understand human language as it's spoken and written. All right. So we have several sentences of text that convey different meanings. What do those sentences mean? If you or I read those, we can kind of interpret them and internalize the meaning and make a decision. But computer programs can't natively do that. If we're talking about math, computing a mean, computing a median, running a linear regression, there's a mathematical formula that we can easily instruct the computer to do, and it'll produce the answers. It's much more difficult when we're talking about natural language. So there's really two sets of approaches that I'll talk about. I'm going to briefly talk about kind of the traditional approach to natural language processing, which starts with this concept of a bag of words. And so I'll describe what I mean by that on the next slide. But a bag of words, by representing documents as a bag of words, it facilitates analysis using dictionaries, right? Maybe we have a set of words, which we would call a dictionary, that we can use to classify or to code different pieces of text. We can even do some statistical tests, maybe with like a text regression, right? And I'll kind of explain what I mean by that. But where the real advancements have made, and where I think NLP is really starting to take off, is advances in machine learning that have kind of updated this traditional bag of words approach, right? And so what these advancements for the most part do is, instead of treating every word or every sentence as kind of the sum of its individual pieces, we vectorize this information. And I'm going to describe what I mean by that. But essentially, it's taking a given element and projecting it into some k-dimensional space. And I know I'm getting a little ahead of myself, but hopefully I can explain what I mean by that. But once we've accomplished this piece, we can go back to some of the traditional machine learning strategies, like unsupervised learning, right? Trying to understand how documents cluster. What are the different topics that are in my set of documents that I'm looking at, as well as classification, which is kind of the classic example of what machine learning has proven to be very powerful. Prediction, right? So if I have a tweet that's saying, this company's terrible, don't buy their products. If I'm that company, I can very quickly see that tweet, code that it means something bad, and try to get to the bottom of why this person said that, right? And so again, the advancements in machine learning make those kinds of tasks possible. All right, so starting with the traditional approach, I mentioned the bag of words. So really what bag of words is it's kind of a colloquial term for this vector space representation, or a term document matrix. Now, usually when I work with one of these, I'm transposing it, right? So I would have the words across the top and the documents as rows, and call it a document term matrix, but the underlying idea is the same. In essence, we have D1, D2, D3, and so forth. These are each individual documents that are in my corpus or my collection of text, right? And so for every document, I'm going to identify how many of each word appear, right? And so we have D1 here, which maybe that's this first document. We see complexity appearing right here, complexity appearing right here, and there's a 2. I don't think there's a second complexity visible here, but there's an ellipse here. So presumably complexity occurs again somewhere else. So this same document has algorithm 3 times, it has entropy 1 time, and so forth. Presumably this document term matrix is continuing, down with additional words. So then we go through and we do this for every single document we're looking at. In this case, we have 5 documents, so we see 5 columns, and the number of rows would correspond to how many unique words appear in this entire set of documents. Now, you can imagine with 5, and I don't know how long these documents are in total, but with 5, you could easily get to something like several hundred unique words, maybe even in the thousands. But often with natural language processing tasks, we're dealing with tens or hundreds of thousands of documents, in which case we could have 10, 15, 20,000 unique words. So often when we're representing um, text in this way, in this document term or term document matrix, we'll say, well, we only want the 1,000 most common words. And we might eliminate words, what we call stop words, right? So words with no semantic meaning. So what would a stop word be? Maybe something like the or a or is, kind of these words that are necessary for proper grammar and for us to understand a sentence, but they're not that important for understanding the meaning of the sentence, right? So we can do some simple filters there, and we'll come up with this matrix that identifies, a set of words in the documents and how prevalent those words are. So once we have this representation, we can do a lot of different things with it, right? We can, this is starting to look like one of those spreadsheets that we saw earlier, and we can do things like dictionary-based approaches, right? Maybe I'm trying to identify documents that are related to, information science or computer science, and so I'm looking for words like algorithm and entropy if I'm more on the mathematical side. All right, so with that, I could look for words like that in my matrix and filter down to the documents I'm interested in. I could also use these words to actually construct measures, right? How prevalent are they within the document? And then finally, I can do a regression with this, right? If you think back to what a regression is, we're basically taking some dependent variable, like a y variable, and regressing it on maybe 2 or 3 or 4 or 5 independent variables. Well, we could view this, these each of these words as one of these independent variables. So we could have a regression with like 1,000 independent variables, but that's okay. There's techniques to deal with that, and as long as we have some kind of response that we're trying to measure, we can use it. So the main downside of this, of this traditional approach is it's probably obvious to you, right? We're ignoring a lot of things. We're ignoring the order of words, right? We don't know where complexity occurs within the document, within the sentence. It ignores word similarities, right? So um, if there's words that are similar, like good and excellent kind of imply some kind of positive outcome, we're treating those as completely separate, right? As basically as independent, because we're not accounting for similarity. And it's harder to account for things like negation, right? If I'm not happy, well, I'm going to see happy in the document, and it's not clear that not is going to be linked to that, right? So it's possible we could have noise from kind of inverting that meaning of happy. So this is where a lot of the advancements have come in. Is as readers, if I read I'm not happy, I understand immediately what that means. So how can we use that usage to kind of understand or help the machine understand what is really meant by that text? So the first example I'm going to talk about is this thing called word Devec, and this isn't necessarily the first advancement, but I think it's one that's somewhat intuitive to understand. And what it does is evident in the name, right? It's taking words and converting them to vectors, right? I'm going to describe how this works on the next slide. But what do I mean by a vector? Well, in essence, so if I have the word, well, I'll just do something simple. If I have the word the, apologize for my handwriting, I'm going to use this model to turn the into a k different numbers. right? So this one could be 0.1, this one could be 0.2, and so forth, right? So I have, k different numbers. With Word2Vec, the traditional model is actually 300, right? So every single word gets 300 different dimensions. And then from that, I can use this in a variety of ways, which I think will become evident in a minute. So this is the method, right? And so this is using, I'm not going to really get into, specific machine learning algorithms, but this is using a single hidden layer neural network. And what it's doing is it's using context words to understand target words, or vice versa. There's actually two different versions of that. I won't kind of get into the weeds on what the differences are. But this is showing you kind of what the target word is and what the context words are. So if I have a window size of 2, right? So I'm looking at 2 words on either side of each word in my sentence, then my target word is wide. The model is going to see road and shimmered and the. So we're going to have 3 different skip grams identified, right? If I move forward to shimmered, I have 4 different skip grams, each one, wide and shimmered, road shimmered, in and shimmered, and the and shimmered. All right. And you can see if I expand the window to 3, I obviously get more. Now, there's a couple important things to point out here. If a target word is a context word, or sorry, if a context, this relationship is directional. And so what I mean by that is if I come down here um, to hot, right, we can see that hot is a context word for shimmered, but shimmered is not a context word um, for hot. All right, so it's learning, in essence, order matters, right? And so this was really powerful in kind of updating the tools that we had for natural language processing, because it started to account for similarities. So I'm going to show you a plot in a second that you're not going to be able to read at all, but I think it'll at least illustrate the idea. So remember, Word2Vec is 300 dimensions. Right? So again, don't try to read this, but I'm going to kind of highlight some things. So we can take those 300 dimensions and collapse them down to 2 so that we can visualize the relationships among words. And so down here you see that, or you don't see, but I can tell you this lower corner is service, services, and products. So 3 words that go together. Up here we have play and games. Over here we have million and billion, school and students, right? So all of these different groupings, they are words that naturally fit together, but the researcher or the computer scientist didn't tell the program that those were the same words. The Word2Vec model learned that through how those words were used. All right. So this, to me at least, was something that really kind of jump started advancements in natural language processing, which moved beyond word vectors. All right. So the big challenge with word vectors is they really worked well at telling you words that were similar, but they failed to capture context. Right. So I think these 3 sentences give you kind of help understand what I'm talking about. So here we have capital, capital, and capital used in 3 very different ways. But Word2Vec is going to develop one vector for the word capital. So advancements such as a long short-term memory network, which is a recurrent neural network, which keeps track of kind of what words were used recently when encoding the next word, as well as BERT, which is developed by Google and really underlies all of their English-based querying now. These are advancements that are somewhat similar to this idea of word vectors, but they're transforming passages of text instead of individual words. So this gets somewhat complicated, so I'm not gonna spend a lot of time talking about the specifics, but I want to finish up by talking about how we can use these transformation of texts in various ways. So the first is in clustering. Now, clustering was developed separate from natural language processing, but what clustering does is it identifies natural groupings of data, or sorry, natural groupings of observations within data. So think back to the Word2Vec model, or you can think of it, from the BERT model, or the, something that's transforming text into these vectors. And we can use some kind of clustering algorithm like k-means, or some kind of, some other model to identify natural groupings. And we can see that these documents fall into these different groups. And then I read the documents and I say, well, this one corresponds to forgotten passwords. This one is talking about NLP. right? So we can kind of quickly understand the different categories of data that we have. Similar to this, topic identification, right? I do want to have times for questions, so I'm going to kind of finish up quickly. But topic identification is similar to clustering, except we want to know within a given document what different things are talked about. And again, using machine learning in these contexts greatly improves the performance of most of these models. And then finally, classification, which I talked to about earlier, and I kind of alluded to this example, but in this framework, we have this tweet here that enters into our model. We identify some keywords, and then we use something to classify what the tweet is meaning. So in this case, we're trying to understand why these customers are angry. These cell customers are angry. Is it because they have no signal, service failure, or low speed? If I'm using a machine learning model to help categorize these, then I can kind of quickly identify the reason for the dissatisfaction and try to address it. So with that being said, thank you for listening. Lindsay, I'm happy to answer any questions that may have popped up.
Thank you, Robbie. I've always wondered how these companies address the angry tweets so quickly. So very helpful. Thank you. Yeah. So can you share some examples of how you've applied these NLP methods to transform unstructured data to insightful, impactful data for your work?
Sure. So actually, I can talk about a project that I'm working on right now with another professor here at Georgia Tech, Eric Condi. So we're looking at we're trying to understand whether information on Twitter could be useful for assessing a firm's risk of failure, right? So Eric has extensive background in auditing. I do some audit research, and so the main question for those that don't know, auditors have to opine on a company's likelihood of the ability to continue as a going concern, which is kind of the inverse of failing, right? If the auditor thinks the company's about to fail, they have to let investors know. And so what we've been looking at is how to train a model to take information on Twitter and on stock twits to say, well, all of these opinions from these investors, are these predicting a likelihood of failure that auditors could potentially use? And we find they are pretty strongly predictive of failure. And right now the information seems to be different than the information that's used by auditors. So that's one example. Yeah.
Very cool. Thank you. And then this is a really interesting question. Are you able to shed any light on how this technology can be used in handwriting recognition? And has it evolved to the point that it can detect fraudulent signatures?
That's a great question. So I think this is my opinion. This is not something that I've tried to do, or I'm not in this arena. But I think where that would actually apply would be in more in like image classification. So image classification is again it's built on a neural network, in some ways similar to the transformer I talked about, but the architecture is a little bit different. But my guess would be potentially yes, if you had a sufficient sample of valid signatures that you could then compare against the fraudulent one. Because what the image classifier will do is basically try to say, is this image you're feeding it, does it look similar to this one? And it'll, it goes, instead of going word by word or sentence by sentence, it goes pixel by pixel. And if enough pixels tend to be off, then, maybe it could work, but that's me speculating.
That's pretty cool. Is Word2Vec what Google uses for its live translate feature on Android devices? If so, how closely do you think we are to having that become common practice in public every day? And is it already being used a lot in businesses?
So I can't answer for sure what the first question is. So Google is always updating. Well, I shouldn't say always updating. I was kind of preparing for this. I was looking at BERT in particular, which is, BERT's kind of their newest advancement, 2018, 2019. So my guess is they might be moving more towards that, which they're more taking context into consideration. Now, if you're just translating single words, that's true. But the broader question of whether these models can be used for translation, absolutely. That was actually one of the early applications of machine learning and natural language processing, was training models to move from one language to another, right? So is it exactly the same as the Word2Vec model or the BERT model? I don't know necessarily that that's the case, but machine learning greatly helps these translation. That's kind of what they're built on, is, instead of encoding all the different rules that you would need to know to translate from English to Spanish, for example. Just give the data, just have a couple pairs of sentences, or not, you would have thousands and thousands, maybe 10,000 pairs of sentences that we know are equivalent, and train the model to understand that translation. I don't know, I'm almost out of time. I don't want to keep anyone past it, but I think it is an everyday use. Like I mentioned that I didn't get a chance to talk about this. So obviously when you go in Google and start searching something, everyone has the auto completion, options that pop up. That's BERT in action, right? So this model that they've developed, that's it trying to guess what you're going to say.
Well, thank you so much. I know we are kind of out of time, so hopefully, Robbie, you can address some of these later on LinkedIn. But do want to thank everyone for joining us today. We're about to take a break for the summer, but we'll be back in the fall with more exciting topics to cover. You can learn more about future Scheller Lunchtime Live sessions by following the Georgia Tech Scheller College of Business on LinkedIn. A recording of this session and future sessions will be available on LinkedIn and YouTube as well. Thank you all for joining, and we're looking forward to seeing you again in the fall.